You should put that one of those days flipping around.
Just they learn a completely wrong thing. All right. What's that? Yeah, I'm sure they'd like that. So here is the rest of the schedule. We are inside of what we call week 12. We're not really on track, but I'm gonna do it anyway. Okay, so we're gonna finish formation of the solar system this week. We'll maybe briefly talk about exoplanets. We'll just like skim them. We've done that a little bit already. We'll do like what's cool about our star. We'll talk about stars, how they are born, how they grow, how they die. We'll talk about what happens to the really massive ones that explode. And we'll talk about our galaxy as a whole. That's already week 15. That's the beginning of May. And then we'll talk about the foundations of cosmology. That is the big questions like, what does it mean Big Bang? And we'll talk about how galaxies evolve. We'll talk about what this thing is called dark energy, dark matter. And this says bonus lecture, but this will probably end up being this. We have a few more labs. We won't be able to do a lab today. If you came in thinking, oh, I'm so excited to do lab today. So sorry to disappoint you. It was supposed to be asteroid sizes. I bought the bricks. I have an idea for what we're going to do for this lab. It's a really great idea. I went to go buy the things that I'm going to use as sieves, and it was Easter. So everything was closed. I forgot about that. That's my bad. So we're going to have a free one today. And we'll do asteroid sizes here. And then we'll do, I didn't move them all down. But we'll do one that is about the different types of stars and where they are in relation to one another. That one's really fun. We'll have a bunch of balloons. We'll blow up the balloons. We'll put them all around. And you'll see like what the nearby stars look like. Okay. Questions, comments, concerns? Yeah.
So week 15, our lab is up there again at those nursery.
Yeah. Hopefully we'll get one that fucking works. You know, I don't know at this point. I appreciate anyone who came to the extremely windy event, but it was awful. It's cold and it sucked. So it was perfectly clear conditions.
Now it seems like a perfect day.
Yeah, it's always right. And of course, if I announced one for tonight, it would immediately start being windy. So
we should just go up there
on a whim, just at any minute,
just like that. And
every single night we should go up there, right?
And then if people see the gate open, then they can just join in.
Okay, so let's get started then. We're going to talk about the formation of the solar system. What do you see? Where's an explosion?
In the middle, or an impact.
Yeah. Is this the real picture?
No.
No, I didn't take this, right? I'm old, but I'm not that old.
Maybe something.
When did this happen? Is this recent? Millions or billions? Billions of feet. Billions, right? So this is early solar system. That's what we're going to talk about today. We're going to combine all of our thoughts into our head. We're going to come up with an idea for how this all happened. Oh my goodness, is this going to go away? All right, whatever. So we talked about impact cratering. Talked about how this sort of leads us to understand when things happen in the solar system. And there's this period called the period of heavy ballpark. We're going to come back to this as an idea and figure out why this happened. But the important thing is that small craters greatly outnumber large ones. And we're going to prove this for ourselves in the lab that we were supposed to do today, but that we will do next week. Okay. All right. So does collisions and impacts, does that explain any other phenomenon that we've seen in the solar system? Potential explanation for collision. Oh, collision caused that. Schumacher-Levy spots, right? We've seen those. Yeah. Saturn's rings is probably the destruction of a moon, the right idea.
What? Axis tilt.
Axis tilt. Our axis tilt possibly comes from the fact that we have, and I wanted everyone's first answer to be the moon. Okay. Another axis tilt would be like Neptune's axis tilt.
Did you see the new pictures of Neptune? I should have included that. What an opportunity for greatness. Okay, possibly spin Venus's spin backwards. People remember that story? I know it was quick at the end.
Not so fast. Or like if the effect was so.
If Venus, if this hypothesis is correct, that this David Stevenson's hypothesis that he's refused to ever publish his paper because it's impossible to prove. He said you could have a moon forming event, just like we have, smash into the proto-Venus and make a moon. Now, traditionally, what will happen is that moon will start to recede, just like ours is. The moon will get farther and farther away. Okay? But if you got hit another time, and you formed a moon that went the other direction, then both of those moons would crash into the surface. And if both moons crash into the surface, there is no evidence for the surface anymore. The surface is gone. All right. So the nice thing about our moon is we can go there and we can grab rocks and we can look at it. We can say these rocks look like mantle. But if you take something from outside of Venus, you stick it under the surface of Venus, good luck. Because you can't even land on the surface for more than 45 minutes. Right? God forbid if you try to get magma. Possible. So we think of it as being untestable. Now, maybe someone comes along in 100 years and proves it, but then you'll just be like, I remember when I heard, right? Or whatever your robot voice sounds like at that time. Okay, so that's Venus. Probably shattered Pluto into Pluto and Charon, and the Mercury's large core is due to the fact that you smashed off the outer mantle. Okay. So in general, when we think about the solar system, we've seen all of this evidence so far. We can boil it down to a few things. We see that the 8 planets lie in a common plane. They lie in something called the ecliptic. Okay? They orbit in the same direction. They mostly rotate in the same direction. And the moon systems do similar things. So for example, if this is Jupiter going around the sun like this, okay, and Jupiter is rotating like this, and we haven't even talked about this, but seen from above, okay, let's say it's like this, Jupiter going around, and now I zoom in on Jupiter, all of the moons go around in the same direction. That's surprising to anyone? It should be surprising to you, because if there was an explanation that did not require them to be going in the same direction, consider for a moment 8 different planets. Okay, they have 2 different directions that they can go. They can go this way, or they can go that way. What are the odds? Flip a coin, you get 8 heads. Big or small? Very small. I'm going to give you $1,000 if you can do it. But you have to pay me $10 if you can't. Would you take it? Yeah. You would take it? That's $10 from him. Guarantee it. Go home tonight and try it. The odds are very, very, very small. In fact, this is very good evidence that, of course, there has to be an explanation for why they're all going in the same direction. Because you would expect it to be random, unless there was a reason for it. So now we need to explain that reason. The same thing is true that there's 2 types of planets, right? Why does it go Mercury, Venus, Earth, Mars, terrestrial planets? And why not Mercury, Jupiter, Pluto, Mars? That's just as fun. Maybe even more fun. How come why not that before? Why not? I mean, we're not touching each other. Yeah. Right? Jupiter's out there, doesn't bother us. Yeah, so we need to explain that. There's 2 types of small bodies.
icy stuff and rocky stuff. Why is some of it icy? Okay, and finally, we have to explain all the exceptions. I already kind of told you a little bit about the exception rule, but we'll see all the ways that it can be different, right? Okay. Real picture, fake picture? You think it's real? Hands up for real picture. It's fake. Oh.
Looks like it could.
But one of these will be real, and then you'll be real stuff, okay? All right. So these things that we have to explain, I'm gonna put them into order here, and we're gonna explain them. First, it's called orderly motions. The fact that stuff isn't doing whatever it wants to do is called orderly motions. Okay? The fact that it's all in a plane, that's weird. Why? The fact that they rotate in the same direction. Even more weird. The fact that all the moons of all the objects orbit in the same direction. Why? Right? And then we'll talk about two kinds of planets. So let's start with orderly motions. Here's what we're going to use. We're going to look at star forming regions. These are the cool pictures that we've never been able to see at the observatory. Go up and see the beautiful pictures of nebula, places where planets are being formed, stars are being formed. But you need, no clouds and no wind. It's never happened. Hopefully it happens before the end of the semester, because that would suck. Okay. We'll look at the solar system. There's evidence from the solar system that we can use. And we'll look at other solar systems. Okay. So let's talk about the formation of the sun. We weren't around for the formation of the sun. Because that's not good. Okay. I wasn't. You're a vampire from outer space, let me know. So what we do is we look around this room and we see different people at different stages in their life. Right? Some of them have hair, some of them do not. There's a correlation there, right? Well, the one with the least amount of hair is on the older side. Right? Tells you something about the life cycle. Because maybe these younger ones with a lot of hair, maybe they'll end up later without hair. Not Kobe. Everyone but Kobe, right? Okay. Or, maybe there's a height distribution. Or there's a size distribution, right? And you can look at all of these different parameters. You get all these different people, and you get them together, and you begin studying them. You look for trends. And so we weren't around at the beginning of the sun, but we do see other stars quite similar to ours. And we see it at every stage of its evolution. And then we can come up with these theories on how it works. Okay. So let's start with some words. Start with the word nebula. Is Latin for mist. Okay. Just means like a cloud. So you used to be able to look up at the sky and just like see a bunch of stars. You can see something called Milky Way. Just looking up. Everyone can do it. Now 20% of people in the whole world. The nebula are just like spots. So if you look, squint in this place near Andromeda, you'll find Andromeda's nebula. Just looks like a faint fuzzy ball. And that's a galaxy. That's the nearest galaxy. Okay. So fuzzy stuff, they just said, I don't know what it is, but it's fuzzy. So it becomes a nebula. And we're really good at naming things. So you'll hear about things called planetary nebula that have nothing to do with planets. Okay. Sorry, I can't change it. Okay. So here's Orion's nebula in the trapezium cluster. This is a stellar nursery. And what you're seeing here on the left-hand side is the wild field camera. And then I think this is in the infrared. This is in ultraviolet here that sees through the dust. So here's what you'd see with your eyeball. And you see these little red boys right here. These are brand new stars. Brand new, like only several 100 million years old. And they are hot, really hot. That they're blowing away all this gas. So you see all this dust here and gas. That's what made them. And then after they're born, they say, I don't want any more material. I don't want it bigger than this. And I get really hot. And they throw a temper tantrum and they get rid of it. The analogy I like to make is like a little kid, and then it makes his room, and then he throws a temper tantrum and throws everything in his room out. Okay, that's what they're doing. Okay. Can you hit the lights actually for me? This is where the cool pictures come back in. So on the left-hand side is the Hubble image. On the right-hand side is JWST. It doesn't look real, but it is real. You can tell that it's a JWST image because of what?
The sixth line.
Yeah. So traditionally, like a Hubble image, you'll see a single cross, whereas here you see this like six-sided triangle type thing. And of course, the JWST is seen in the infrared, so it is able to see through some dust types, whereas here you can see some more structure. You see in here this like little circular thing. Okay, that's like a new star being born. It's forming this little bubble from the dust that it was born into. And you can see it over here, very bright. Right? Same thing's true here. These ones here have already carved out a little space for themselves. Okay. You can break down that picture even further. We have these beautiful young star inside of a globule. It's just being made. This one's cool. Oh, I should have pointed that out. Yeah, all right, whatever. It's over here. Young star, the disk inside its cocoon. What? Okay, let me say this again. This is the material that it's being made from. It's cocoon. This is the young star in there. And then it looks like there's this like flat boy right here. If you look right there, it kind of looks like a little jellyfish. Not. That size, for example, this size here is the orbit of Neptune. And let's remember, anytime you see a dot like this, you are not seeing the star itself. It is impossible with current technology to ever resolve a single star other than the sun. But you have this beautiful filamentary structure. It all looks fake. Okay. You seen this one before? Yeah. Okay. This is called Pillars of Creation, the Hubble image. And this is gas and dust, mostly dust, I believe. And what's happening in here, you have this place where the gas clouds are collapsing. And as they collapse, they form new stars. Let's look with JWST, and it allows us to look through the dust. And so, for example, here's that same star over here, right? You see the matching up of the star? But if we look inside of this now, in here, now I start to see stars that are still obscured coming to light. Stuff that's covered in dust. Once the dust is blown away, we'll be able to see it. What I'm trying to sort of bring home here is the idea that gas and dust is just this clumpy stuff that sits out in the intergalactic medium. And for some reason or another, it collapses. And as it collapses, it forms stars. And we can see evidence of it. Baby stars just forming from dust spontaneously. Yeah.
Is the dust like dirt dust? That's the same thing. Different type of dust.
Very good question. And we're not going to go into the type of dust. Think of dust really as what's the best way to talk about it? Anything that's not gas. Does that make sense? Okay, so gas would be like atoms and ions. Those would be gases and plasmas. Dust is like everything else. Yeah, I know. Okay, you have to bear with me because astronomers are the worst. Okay, and we'll talk about this when we talk about the astronomer's table of elements. For example, what is a metal to an astronomer? You'd think so, right? That would be sensible, right? A metal to an astronomer is anything that's not hydrogen and helium. Correct, that's the right face.
So oxygen can be considered a metal to astronomy?
Exactly. It's outrageous. It's a crime against us understanding things. But for the purposes of what we're talking about, dust is, it can be like, you can think of it conceptually as anything that's not in the gaseous form. Right? And there's mixes of different dust with many different types of properties. And it fills in the cell. And when we talk about where dust comes from, why there is dust all in between stars,
it'll make more sense why I'm being so ambiguous about this, right? Because we haven't even said where does this stuff come from. Okay. Question?
So would you like saying anything that's dust is anything solid in the universe? Where you can say like anything that's gas is just like atoms or just like.
Yeah, solid is a little tricky. Right, because everything can be a solid at the right temperature and pressure. These are just like not hydrogen units. It's very stupid, I'll show you. Okay, here's another example. So this, again, I'm gonna go back to the spot. Where does our sun come from? Probably something like this. So it's just like this cocoon of dust. And once you sort of peel back the onion with JWST, you can see right through that dust. And so you go, oh shit, there's a cool little star like right there. Bada bing, bada boom, right? One. You can kind of see it. It's the same one. All right. So this is forming a brand new star. All right. All right. Actually, I don't think this is JWST. I don't know where this is from. Supposed to be. No idea. Okay. Here's the Keyhole Nebula. This is one of my favorites. Okay, that's a generous interpretation. And if you look, this piece here, you can see what we were talking about before. Like clear out their stellar nursery, they have an antrum after they're born. They blow away the gas and dust. It's literally what's happening. These gassy filaments are being blown away by a brand new star. You can see that here as well. You have a brand new star. The gas that formed it says, I don't want to be a part of you anymore. And it's going to go. Yeah. Pretty cool, right? What's that?
It looks like a cell.
Yeah, mitochondria right here. Okay. Get it? This is the powerhouse of it. All right. Hold your applause. Okay, so let's go back to the building blocks, right? Where do the elements in the solar nebula come from? The stuff that we use to make our planets. We currently are made of like what type of elements, by the way? Carbon, good, we know that. Nitrogen, oxygen, hydrogen, not mostly iron though. There's one that's more important. You've got the CHON, and there's P and S that are really important. Awesome. Phosphorus and sulfur. Those are really important for life. That's called chunks. Just what you need to make DNA and everything happen. Okay. But where does that stuff come from? So where does the H and the O come from? Where does the H and the O come from? So if you don't drink water, you don't. You don't have any more H. Okay, what else? Where does the C come from? Air we breathe? We breathe in oxygen. We're dangerous. It's okay. It's okay. No, if we breathe in carbon dioxide and we used it, we'd be in great shape. In fact, we expel it and it's a poison to us. We eat it. Correct. Good. Nitrogen, same place. All right. Phosphorus. All right, but where did it come before that? Stars. Bold assumption. Right. Bold assumption. Okay, so let's find out how that happened. So here's the periodic table of the elements. Everyone's memorized this? Okay, I mean that good because I hate chemistry. But they have some fun little features. Okay, this is the hydrogen. Okay. There's beryllium. Okay. Lithium. Lithium is a medication, make you feel real weird. Okay. B. Boron, very good. Carbon. oxygen. And look at them, they're all right next to each other. They're all so yummy. CNO. Good. Cyno. This one? Okay. And this whole line is supposed to be special, right? What's that? Noble gases. Do they like to participate in chemistry? They hate it. They'd rather die. You can't form anything with them. Okay. So this is what we need over here. A little bit of these guys. So look, oh look, you get all of them right here for free. And this. Okay. Okay. One fun one's down here. What is this one? All right. You have to know this one, right? Look in California. What's this one?
Einsteinian.
Good. Very good. What's this one? Americanium. Very good. What's this one?
Plutonium.
That was a good one. Boom. Okay. All right. Let's see if we can. Enough. So this is the astronomer's periodic table. So much easier. Doesn't that you only have to remember right after the Big Bang, you just had about hydrogen and some helium that was formed in the Big Bang. And that's it.
Imagine this on as your final exam.
This is the final. Okay, so right after the Big Bang, you only have two elements. And in order to get any of the rest of them, you need stars. Okay? So what happens is very straightforward. You build stars. They turn hydrogen and helium into heavier elements. And then they explode, sometimes violently. And they toss their refuse back into space. So the gas and dust that brand new stars are blowing away, the gas and dust that they form from is the excrement of dead stars. Okay. So when you breathe in, you're breathing in oxygen, nitrogen, and it's all formed in the interior of stars. Okay. So this is what it looks like today. Hydrogen, helium. You know, small. Okay. Neon, there's a good amount of neon. Some magnesium, some iron, silicon, sulfur, argon. Okay, about 2% of everything else. That's why it's designated as a metal. Because by weight, absolutely. So if we looked at the astronomer's periodic table in 13 billion years from now, in the future, how would it look different? Is it A, going to be exactly the same? B, H would be a little smaller, but not by much. The other element's a little bigger. H and E would pretty much be gone, all converted to heavier elements. Or all the elements would be the same size, same amount of everything. Not the same as now, but the same as each other. Equal amounts of everything. You know when you're ready? Vote on 3, 2, 1. Okay, interesting. We want to defend their answer. Yeah.
It would be exactly the same, right? It's a cycle, it always goes back to when it came from.
Okay, interesting. Okay. Any other arguments?
Sip B, I feel like there's more stars to be formed, but not like a significant amount,
Okay.
like in the shipments.
Okay. Any other choices? There's people chose these 3. No one chose this. No one for this? Let's go back 2 steps. So this is what it looked like at the beginning. Hydrogen and helium. What creates carbon, nitrogen, and oxygen?
But what does it? What does the job? Stars. Okay, so we need stars. So 13 billion years of evolution. You get that. And this is how much CNO you make. So we wait another 13 billion years. What happens? Slightly larger, slightly less. Maybe double, maybe not. Right? Did we make any hydrogen? Do we know how to make hydrogen? Big Bang. Big Bang's the only way we know how to make it. So the only way that we can make this into a true cycle would be if we restarted the whole universe. We're not going to do that as far as I know. Okay. There might be an off switch. No. All right. So that's what it would look like. Still mostly hydrogen, but slightly less, tiny bit more helium, and a little bit more of everything else. Now, if you say to yourself, that's imperceptible, Mateo, I agree. They look the same to me. You have to wait many, many billions, hundreds of billions of years before anything finally happens. Right? Eventually you get to something called the heat death of the universe, but we won't talk about that at all. Okay, we're going to really briefly talk about some conservation laws that we need in order to understand how we form a solar system from a bunch of gas and dust. So we have all this gas and dust just sitting around, and somehow that explanation is going to tell us that the planets go in the same direction. That seems like garbage, right? Yeah, good. Nice skepticism. So let's talk about the conservation law. First, how does an ice skater spin? What do they do to spin faster? What's that? Yeah, but what do they physically do? Pull in. Okay, so what did you do? You took your arms from out, pulled in. What does that mean? Pulled in. What have I done?
Your moment of your mass is being pulled towards yourself.
Right. So the moment of inertia change, what that means is that the distance between the arms became shorter. Okay. And the angular momentum is conserved, so it's been faster. And we'll also talk about, does energy come from places? In a cosmic sense, can I just generate energy? No. So when you're scrolling on Instagram and there's a perpetual motion machine, all you have to do is invest now $15. You say, no, not where's my credit card? Okay. All right. All right. So there's the conservation of angular momentum, which simply states objects that are rotating maintain this quantity, that the product of their mass, their velocity, and their radius is constant. So if I change my radius, the radius at which I'm orbiting or rotating, then the velocity or the mass have to go up to compensate. Okay, that's why you spin fast. So if you were an ice skater and you had big, really bad food the night before, you're spinning, and you start throwing it all up, and your mass goes down. Would you spin faster or slower? Faster. Right? Good analogy, right? Sort of the opposite of what you expected, and you might be a little bit awake now. Okay, so is this process problematic for anyone? We're all good with this. We're not going to spend time on it. So we're going to pass that. We're going to pass that. Energy. We already talked about this briefly, right? Energy in gets converted into potential energy. Kinetic energy becomes potential energy. And then you can use it again as kinetic energy. But you can't generate it. Right? Everyone remembers this discussion? Sun is the only form of energy that matters. Beer is sun. Your phone is sun. Fritos is sun. What else is sun? Anything else on there? Oil is sun. That's a fun one. Did you know that? How is oil sun? Oil is dinosaurs? Yeah. And dinosaurs is grass, and grass is sun. Give me another one. Fossil fuel. Everything is sun, except for a few things. Wood is sun because wood is grass and grass is sun. Anything else?
Waves.
What's that?
Waves.
Waves. Okay. Waves is wind, and wind is sun. Anything else? Metal is not energy. But if I throw metal at you, then you get energy, that's gravity, right? So you can use like, pendulums falling to convert between kinetic and, potential energy. Anything else? Can we get this then? Okay, so angular momentum is gonna be conserved, and we're gonna conserve energy. Now let's use these two properties when thinking about the formation of the solar system. Okay. So we start with a clump of gas. Okay. Bunch of gas, very big. Okay, and eventually, very middle, you form a star. What causes a gas hub to collapse? Has a really bad day at the office and breaks down emotionally. What's that?
The biggest piece of dust has gravity.
The one single piece of dust causes the rest of it to collapse.
Well, one by one, right?
Right, so you're thinking in the right direction. So as a piece of dust gets bigger, it's gonna attract more dust to it. That could be a runaway process. That's when it's already started collapsing. But what might trigger the collapse of the gas bubble?
Temperature around it?
Sure, temperature on it. There's a couple ways to do that. Let's say you start with a big gas cloud, and then nearby, let's say a star passes by. I mean, these scales are huge, but you can think about it that way, right? Star passes by, causes a wave. That wave causes the collapse of the gas cloud. Or maybe a star explodes nearby, and it lets out a ton of heat, collapses the gas cloud. But once it starts collapsing, it's a runaway process. Positive feedback. Because now as I concentrate mass at the middle, now more stuff wants to go to the middle. Make sense? Okay. So as long as I can get a tiny bit of it to collapse, we're good. And then I'll get a star, probably. Okay. So this is what it's going to look like in a cartoon form, right? Again, not a real picture. Important to remember. So here we're gonna have three things happen. It's gonna spin fast. It's gonna heat up, and it's gonna become a disk. We're gonna talk about all three of them. So why does it spin faster? Yeah.
Conservation of angular momentum.
So in the analogies that I used for our ice skater, which of the two is correct? The throwing up or the arms? Okay. Making sure you're paying attention. Okay, so that's the angular momentum conservation. Why does it heat up? More energy. Why does it have more energy? How did it generate energy?
Gravity.
What do you mean from gravity?
So like since it has more mass, it would have more gravity, causing things to like.
But think about it like this, okay? So I take a big gas button, okay? Now everything inside my hands is gonna become my gas button. So even when it's out here, it's the same mass as when it's in here. But I'm claiming that the sheer process of coming down here makes it heat up. People disagree? Yeah.
Well, I know that, for an enclosed gas, right, if you change the volume of it, temperature goes up, but is this really enclosed?
It's a very good question. It's a weird way of thinking about enclosed, right? So let's think about heating for a second. Okay, so this really accurately drawn picture, right? These are the gas clouds. It's exactly what it looks like if you look closely. Brown. Gas and dust is brown. So I drew it that way. And then you have these little atoms. They're all moving around, whatever, they're chilling. Okay, in general, they're not really banging into each other too much. And if they are, they're banging into each other very slowly. But now, like you said, let's make the surface or the area smaller. As you shrink it, they bounce into each other more. And in fact, that gravitational potential energy, just like you were talking about, becomes kinetic energy of the individual particles. And the individual particles we can think of as the thermal energy.
So even though the whole thing itself is not moving faster in one direction, the ball's still staying here. Collapsing the gas into a smaller ball increases the temperature in the ball, so to speak. It's not a ball, gas bubble. Everyone love it? Okay. Why does it flatten into a disc? I'll guarantee you almost no one will get this, but you want to try anyway because it's fun. What's that? Dark matter. That's a bold one.
I don't have an explanation, but I kind of have like an analogy,
Okay, what's the analogy?
like spinning a pizza. or
Yes.
pizza.
Okay, everyone says spinning a pizza. It's wrong, but I love going there because we need to obviously think about what we know and why Mateo's analogies aren't always great, right? So sometimes space is really different in ways that we can't understand, right? And we'll see why spinning a pizza does have exactly the same shape, but for a different reason. It's weird. The same shape, different reason. Okay. So why does it flatten into a disc?
The way to spin.
So it is spinning. Spinning is important, good, but not quite.
What it's made of?
What?
What it's made of?
What it's made of? Do you think like the compositional changes make it flat? Okay, okay. There might be like there's stuff in there, right? Think about that in a few seconds. Okay. So some people say that gravity, no one said like gravity flattens it. It's okay. Almost everyone always says flung out. All right, they think about like centripetal acceleration. If you're spinning something, like if I don't have like a string, but actually I do have a string. Okay. So like spin this. Whoa. And make a circle, right? And the reason that that happens, right, is because it's being flung out, but it's being held onto. So when I spin my pizza dough, right, there's surface tension in the pizza dough. It gives it the disc shape, and that's wrong. You're like, why even say it, Mateo? Okay. So gravity is pulling the material in to a ball shape. Okay, that's weird. It's not a ball shape. Gravity's broken. And the disk gas particles are on simple orbits. What I mean by that is when I eat pizza, it's delicious and tasty because of gluten. And that's a long chain polymer, like a sugar essentially, that's in the bread, that holds the bread together and makes it sticky. That's not how gas works. Gas is not made of bread. So it's individual pieces of gas, hydrogen and helium. All they're attracted by is gravity. Everything else, they're totally disconnected. Fluid. So if you were to spin water like this in your hand, what would happen? Go everywhere, right? And that's exactly what we're talking about here. And yet somehow, on these scales, it doesn't go everywhere, it becomes a beautiful disc. Okay, so here's how it happens. As the gas nebula collapses, these clumps of gas collide. What? Okay, let's think about it this way. Let's say you're living your life, you're like a rock or whatever, piece of dust. You're going along, you're having a really good time, okay? And then you pass like a region where there's a slightly more stuff. Okay? And as you try to cross through a busy intersection, if you're walking with everyone in the busy intersection, you're unlikely to get bumped. But if you tried to like walk through it sideways, or even worse, go the opposite direction, like you're swimming upstream like a river, okay, you're absolutely gonna hit something. There's enough people, they'll start dragging you with them. That's the analogy. Okay. So randomly, some preferred direction will appear. And just because of collision between the gas and dust alone, you'll get a disk that will enforce common motion. So anything that tries to leave the disk and go on its own merry way will have to start coming back through the disk. And as it comes through this thick disk, it smashes into it, collides, and becomes dragged along into this disk shape. Okay? Kind of unique. But now we fully understand it. Disk, I got it. Right? So spinning causes by conservation of angular momentum. Hot causes compression. And the disk cause is just from being forced through common motion. Okay. We're gonna come back to forming the star later, but let's see if this is true. So in fact, we can look around. This is called the nebular theory, the idea that stars and planets form in a nebula. They form from the gas cloud. And on the right-hand side, is this a picture? What's that? A collection of pictures. These are real pictures. Every single one of these is a brand new star. And around that brand new star is something really dark if you squint. Okay? So look right here. So you see the star? And the dark thing is dust. And if you look at it from the side here, you see how it's like a bright thing, and then it's got like a dark thing across it? That's like looking at the disk like this. Edge on. You'll see many examples of it. So there's the disk on a side, there's the disk from above. When we look around, we see tons of disks. There's the disk from above. You can see it like carving its way through its solar nebula. You see the little gas cloud it made? Oh, these baby stars. Look at this one. Right? You have to get it sounds because there's no sound in space. Okay. Oh, you broke me. Philip's computer. For real, for real. Okay. What about this one? Real picture?
Yes.
Is it? Raise your hand for real picture. Raise your hand for fake picture. Real picture. Okay. So this is an exoplanetary system, a planetary system outside of our solar system. You have a protostar. It's a brand new star. When I say the word proto, it just means baby. Okay, baby star. And you have all these gaps in the disk. We'll talk about how these gaps form. Hint. That's what planets are. Cool, right? You can see it. Nice. Okay. Okay, so that was the first one. Orderly motions. Questions? When you get home tonight, your mom's asking you, what'd you find out about orderly motions? I've always been so curious. Now you know what to tell her, right? That happens to you every class, right? Yeah, I'm sure. Okay. So why are there two types of planets? Why does it go Venus, Earth, and not Venus, Jupiter? Or Venus, Uranus?
Well, the four smaller planets are made of like heavier elements.
Okay.
So I don't know if like the analogy of like heavy seams and light falls into.
Okay, I like that. I like that. It's definitely like an outside of the box way of thinking about it, right? There, would your answer change if I told you at the center of Jupiter is like a 30 Earth mass planet that's just covered in hydrogen? No, okay. Any other explanations? Why two types of planets? Why the ordering? Yeah.
Maybe it's the way they're born, like the way the sun was created and the leftover ingredients of the outer part of it.
Okay.
Didn't have as much solid.
Oh, okay. So what you're saying is like the stuff that it was made of matters. Okay. Any other questions? Thoughts?
I don't know if this has too much to do with the window here, but this is always something that bothered me was, how is it that like the first 6 planets are so relatively close to each other, like in terms of orbits, but then Uranus and Neptune are so far out compared to like the rest? What happened there?
Good question. Not part of what we'll talk about, but it is a question that we will get to when we talk about exceptions to the rules. Because in fact, they probably all started quite close. And those 2 that you just described, something weird happened. We will have to explain that later. But that doesn't explain why we have big planets far and small planets close. And why it isn't small, big, small, big, small, big. Or even cooler, big, small, big, small, big, small. What if you had a bunch of eclipses of it?
Is it because like the less dense ones, they like fly faster away from the sun?
What do you mean less dense? What does less dense mean to you?
Lighter like this.
Oh, lighter what? Lighter planets?
Yeah,
Okay, oh, you're saying so like the current Jupiter, current Saturn are less dense than the rocky ones?
yeah.
And so they have moved?
Yeah.
Okay. So why are their moons made of rock and metal? I'm just saying, you gotta poke a little hole just to see if it works, right? We always want to try these, it's an interesting thought, right? We have to remember there's all these pieces of information that we'll have to figure out. Because we're gonna have 2 types of small bodies, that's the second one that we have to address. Right? We have like asteroids close and icy KBOs far. Yeah, let's look at something really quick, okay? I wish that I could read that. Super helpful. Okay, so the top word up here is example. That one you can see. This one says condensation temperature. Okay. And what it means is, you can kind of think of this as the opposite of evaporation. So evaporation and condensation happen at the same temperature, but depends on which direction you come from. So let's say you start at room temperature and you bring a piece of iron up to 1,000 degrees Kelvin. It will boil and it will evaporate. Okay. Similarly, if you take a gas cloud that's 2,000 degrees Kelvin and you cool it down, then metal will condense out and it'll start snowing metal. Is that analogy good? Let's move up now. Rocks, say olivine, okay? I can evaporate it, okay? At a very reasonable temperature. It's only 500 degrees Kelvin, okay? Let's keep in mind, this is not Fahrenheit, it's Kelvin, okay? And these minerals, they'll just evaporate right off. Or if they're already in a gaseous state, then I can condense them and I can make olivine rain. Or what's everyone's favorite mineral? What? Calcium? That's an element. Do you have like a, like table salt? Table salt is a mineral that I like, right? Because I want like a combination of one, right? So let's take table salt and we'll get it to condense out of the air at about 500 degrees Kelvin. Okay. What's this one here? Water, good. And this one? Nothing. These are your ices, okay? And they're called hydrogen compounds because they all share the fact that they have hydrogens. And notice they're friends. Ooh, interesting. CNO. We saw that before, right? Special, special. Okay. And these all condense at less than 150 degrees Kelvin. What about hydrogen itself? Never condenses. Helium hates chemistry, doesn't even want to be included on this figure. Okay, so it never condenses in the nebula. And you might be saying to yourself, Mateo, water does not condense at 150 degrees Kelvin because it is currently way above that and it's not evaporated in my cup. What's the difference here? What's that?
It is how it's diluted.
Yeah, pressure.
Pressure. So remember, this is in the disk. Right, we're in the vacuum of space where there is some pressure, but not a lot, very different condition. Right now, it's nice, we have pressure and we don't die when we breathe in, right? If we were breathing in the disk, we'd have a really bad day. Okay. Let's look at the relative abundance by mass. Wait. Okay, here's a question. Everyone's paying attention, right? I broke it down really well and everyone understood it perfectly. Okay. So at 500 degrees, what exists in solid form? In the disk. The A, metals, B, rocks, C, metals and rocks, D, hydrogen compounds, E, metals, rocks, and hydrogen compounds. When you're ready? Vote on 3, 2, 1. All right. Why don't you ask your neighbor what they got? Go ahead, same thing.
Yeah.
What do you- Excellent. What'd you get? Why? And we'll fix it. Yeah. You all agree?
When you said that, like, it's
100%.
Yeah.
You want to do that?
I believe so.
You're gonna speak up, right? Yeah, let me explain it. You said you all got it. You can explain it?
I mean, I'll say what I think.
Okay, good. Okay, let's revote. Vote on 3, 2, 1. Oh, interesting. All right. You all convinced each other in the front. You're still very ambiguous in the back, and you're all the same on this side. But all 3 of you have different answers. Does someone want to walk through the reasoning?
I want to answer this question if I had it say on the homework or.
That temperature is the minimum temperature for it. For that example to exist in a solid form, condensing is solidifying, so anything cooler than 1600 Kelvin, but above 500 Kelvin in that range would solidify. So rocks and metals would solidify.
Okay. And you don't think this would be, melted?
Yeah.
Cause it's too hot?
Yeah.
Okay, so it's metals and rocks. Because some rocks, for example, can condense or sublimate at 1300. Right? Yeah.
So then when it's saying, and the rocks, temperature from 500K to 1300K. So at 500K, that's the threshold when they would start to like melt and stuff?
Evaporate, yeah.
Evaporate. So there are certain rocks that can surpass that and stay solid.
Exactly. Exactly.
Or not.
Yeah, and you'll notice there's a little overlap. All right, and you're like, Till, don't talk about rocks and metals together. That's fine. You're right. Probably. When you think of metals, and you think of, like you said, calcium was your favorite, right? That's an example. Usually when you think of pure elements,
you think of something like a diamond, for example, obviously we all understand that that is in fact a mineral, but it's like a pure mineral. Okay? It's very different than something like olivine. So olivine is, probably every geologist's favorite mineral, and it's green because it has magnesium in it, and has other stuff in it too, but it's got a whole bunch of crap in it. Minerals usually have a bunch of stuff in them. But plants like minerals have stuff. Table salts, got a bunch of stuff in it. Okay. All right, let's drop the temps. At 100 degrees, what exists in solid forms? You know when you're ready? Let's vote on 3, 2, 1. Okay, so I got mostly 4s. Oh, I got some 1s, 5s, and 3s. I got everything but 2. Want to explain something here? Yeah.
At 100K, everything's like almost frozen, so there's no like. In terms of gas, there's no like particles like bouncing around each other. Everything is such low kinetic energy that everything's all condensed and
Mhm.
frozen basically, so all of that will basically be solid.
Okay.
Disagree a little bit. I said 4 because hydrogen and helium, they stay in gas.
There's a trick answer on that. Everyone saw everything, they're like, got it. But in fact, hydrogen and helium never condense, regardless of the temperature. So the only time you can get helium to condense, you can supercool it, really cool. Has wonderful properties like no viscosity and superconducting properties. But you have to do it at like 13 degrees Kelvin. That just doesn't happen in the nebula. Okay. So in fact, it's D, metals, rocks, and hydrogen. So everything except the stuff that can't, right? Okay. Oh, I didn't put it here. Let's imagine that we are gonna do a lecture draw. Can you hit the lights? Can you hit the lights? We're gonna try and relate here. Temperature and the location the planets on. Oh, does it? Yeah, we got it. I did.
Yeah.
We'll try and do this one like relatively quickly, and then I'll just give you like 6 or 7 minutes to try it. We can finish it Wednesday morning.
5 minutes.
What?
This went 5 minutes?
5 minutes, yeah. I got time.
So. Basically all this. It's way harder to do this.
Hold on. The reason this is up is what we're learning.
I'm thinking of water is depending on the large definition of it.
Well, that would be like, we don't know the composition.
Like,
That's why.
Yeah.
But kind of more easy kind of fifty-three where you can. But you can't really tell what the big ones are. You can see in other ones, it's like much bigger. That's probably just the water.
I think it's not gonna be, but I think it's the thing. Cause like. So above 150.
Water than water, anything up.
Our boy. No, I mean like.
Oh, yeah. We went on.
I think, I don't think it was.
I just let it go right here or whatever.
Yeah.
On Thursday. It's okay. It's like.
Oh, yeah.
Clouds is not clouds.
Real cloudy up there.
Real cloudy.
I think. All these planets.
All that.
Wait, I can't. Yeah. Might have not that it's about, the following two astronomy courses. So these are like some of the assigned, 33.
Good question. I think it either will be taught next spring or next fall.
I found.
Not this fall, but the fall. So it'll either be, yeah, here's these. Spring 24, fall.
Also be.
But it'll be like this, but it'll be harder.
Okay, does everyone fully understand it? We're gonna pause really quickly. Okay. Let's make the planets. The idea here, sun's hot. Close to sun, hot. Far from sun, cold. So there's a temperature gradient in the disk. It's hot in the middle, it's cold far away. And the condensation of all of these different objects determines what you can make it out of. So if you want to build out of hydrogen and helium compounds, you can't do that. Sorry, if you want to build it out of hydrogen and helium, you can't do that. If you want to build it out of helium hydrogen compounds, you can only do that when the temperature has gone below 150. So you can't do that in here, right? And rocks condense almost immediately, so you're fine. Right? Okay. And there's this line up here where the temperature is about 150 degrees Kelvin. We call it the frost point, or frost can condense. Okay. So you build everything inside of this frost point out of rocks, and you build everything out here with everything. I haven't told you yet how to trap hydrogen and helium yet, but you will be able to. So let's look at the relative abundance by mass. When we think about all of these different things that exist in the nebula, most of it is hydrogen, right? Just like we saw before. There's a lot of hydrogen compounds, not so much rock, not so much metals. So if I want to build a planet from only rock and metal, compared to if I have hydrogen compounds available, which ones can be bigger? Hydrogen compounds can be bigger, right? Just in sheer mass, they're larger. So this already explains something, just immediately. Why rocky planets are smaller. There's less shit to build with, right? Now we haven't yet explained how you get hydrogen into the core of those things. That's a trick. But the sheer availability of hydrogen compounds allows the planet to get large, right? If I can make something from ice, I can make it, let's see, that's 1.4 compared to 0.6, making it almost 2.5 times bigger. That's crazy, right? Cool. Okay, so let's use this in action. Oh, that's a lot of words. Okay. Astronomers have discovered massive gas giant planets like Jupiter orbiting at stars closer than 0.7 AU. That's about the distance of Venus's orbit. Why don't astronomers believe that these gas giant planets originally formed at those locations? Is it A, the planet's gravity would be far too large to form that close to the star? B, the temperatures in the early solar nebula were too high at these distances? C, the orbital periods are too long for them to be located that close to their companion stars? D, a young star's solar wind would have blown the planets further away. Know when you're ready? Let's vote on 3, 2, 1. I didn't get anyone? Well, that doesn't feel good. What, I taught you too well? Didn't even trick you into getting the wrong answer anymore? Yeah, okay. So the temperature in the early solar nebula was too high at this point. So they can't form it, because we can't form anything out of hydrogen compounds. So let's talk about how you would make little baby things into big things. So you start with dust, like this, and it turns into a planet. Okay? So first you start with small things. And that small stuff sticks together to make larger things. That's called accretion, right? The big get bigger like a snowball, or like capitalism. Okay. All right. Then really big things, they're like 10 to 20 times larger than the Earth. They are like mega corporations. and they start buying up all the other corporations, right? Removing all of the competition. And they're funneling in all of the users to the tech industry, right? In this analogy, hydrogen and helium starts to be siphoned off. It doesn't have to condense anymore, just grabs it from space itself. So you have all this gas and dust, and where you normally had to clump up and stick at the beginning, clumping up and sticking, now if you get really big, you just draw it in.
So like Uranus and Neptune broke compared to Jupiter and Saturn.
Well, compared to us, they are very rich. But compared to Neptune and compared to Jupiter, yes, they're like Warren Buffett compared to like Jeff Bezos, right? You know all of those billionaire net worth. They all have way more money than us, but there's a hierarchy among them, right?
Or Mercury.
Mercury's like my dogs, no money at all. Okay, all right. So objects outside the frost line had ices, and that really helps you to go from this location here into this one, because we can't get to 20 Earth masses. If you add up Mercury, the Earth, Venus, Venus's moon, Earth's moon, Mars, Mars's 2 moons, and the asteroid belt, you still don't get to 10 times the mass of Earth. You get like 6 or 7. So even if you took all that stuff and you condense it into one planet, it still wouldn't be big enough to start grabbing hydrogen. And you can only do that once you have hydrogen. Okay, we're gonna come back to this idea, and we'll get more into the weeds, and we'll talk about how to form all the planets on Wednesday. Questions, comments, concerns? Cool. Thank you. Yeah, perfect. Thank you so much.